In this video, I want to have a look at solving trig equations that involve sums and differences of angles or double angles. So our first example asks us to solve sine 2x equals 3 cos x in the domain 0 to 2 pi. So the first thing I'm going to do is rewrite this sine 2x using our double angle formula. So we know that sine 2x can be rewritten as 2 sine x cos x. So we're going to have that equal to 3 cos x. Now if I pull that all over to the left-hand side, I'm going to have 2 sine x cos x minus 3 cos x is equal to 0. So to solve this, I'm going to factorize, and my common factor is that cos x. So I'm going to have cos x outside of 2 sine x minus 3 is equal to 0. So that means I'm either going to have cos x equal to 0, or I'm going to have 2 sine x minus 3 is equal to 0, which would mean that sine x is equal to 3 over 2. Now we've got to solve both of those. If we have a look at this one first, we know that that's not going to have any solutions because sine varies between minus 1 and 1, and 3 over 2 is 1.5. So there's no solutions for that. But this one there will be. If we draw a quick sketch of our cos graph, we know that it comes down to minus 1 and back up to 1, and that's over the domain 0 to 2 pi. So it reaches minus 1 at pi, so this value here is pi on 2. And this one here is, I'm not going to fit that in there properly, but that's going to be 3 pi on 2. So our solutions for x here are going to be x equals pi on 2 or 3 pi on 2. So there are two solutions that make this equation true in this domain. Our second example asks us to solve cos 2x cos pi on 6 minus sine 2x sine pi on 6 equals minus 0.5 in that same domain of 0 to 2 pi. Now if you have a look at the left-hand side of that equation, you should be able to recognize it as the expansion of a cos angle sum. So we could rewrite that as cos of 2x plus pi on 6 is equal to minus 0.5. So that's our angle sum. If we were to expand this out, we'd get that. All right, so now we can solve this just as a standard equation. So if we let x equal to, well, let's not use x because there's already an x in there. Let's use theta equal 2x plus pi on 6. Then our equation is going to become cos theta equals minus 0.5. Now that's going to change our domain though. So our domain is, if we changed it to 2x, it would be between 4 pi and 0. But we want 2x plus pi on 6. So we're going to have it between pi on 6. And that would be 24, so 25 pi on 6. So that's what our theta is between. Now to solve that, from our all stations to central diagram, we know that cos is negative, so that's in our second and our third quadrants, and we know that our related angle is pi on 3. So that means for our answers for theta, we're going to end up with 2 pi on 3 and 4 pi on 3. So that's going around 1 revolution, but we're going to have to go around 2 revolutions. So then we're also going to get 8 pi on 3 and 10 pi on 3. So that's our second revolution round there. Now that means that instead of theta equals all of this, we know that theta is 2x plus pi on 6. So if we subtract pi on 6 from all of those, we're going to end up with 2x equals 3 pi on 6, 7 pi on 6, 15 pi on 6, and 19 pi on 6. And then we need to go through and divide them all by 2. So we're going to end up with 3 pi on 12, 7 pi on 12, 15 pi on 12, and 19 pi on 12. Now just to simplify those answers, a couple of them can be simplified down. So I'd end up with pi on 4 for my first one. That 7 pi on 12 isn't going to change, but the 15 pi on 12 could be simplified to 5 pi on 4. and 19 pi on 12. That should have been a 12, not a 2. All right, so in this domain, we have 4 solutions to that equation. Our last example asks us to solve tan of theta plus pi on 3 equals minus tan theta in that same domain of 0 to 2 pi. So the first thing I'm going to do is expand this out. So I'm going to have tan theta plus tan pi on 3 over 1 minus tan theta tan pi on 3. And that's still going to be equal to minus tan theta. Now to start solving this, I'm going to multiply both sides by that denominator. So the left-hand side is going to stay as tan theta plus tan pi on 3 is going to be equal to minus tan theta, so I'm timesing that by the 1, and then times minus tan theta by minus tan theta tan pi on 3. So I'm going to have plus tan squared theta tan pi on 3. Now tan pi on 3, we know what that is. That's tan of 60, and that's going to give us the square root of 3. So this is going to become tan theta plus root 3 equals minus tan theta plus root 3 tan squared theta. Now I want to move all of this onto one side of the equal sign, but I want to keep this squared term positive. So I'm going to end up with root 3 tan squared theta. Now I've got a minus tan theta here. That's a plus there. Just trying to figure that out. It looked like a minus 1. I've got a minus tan theta, and I'm going to minus another tan theta when I bring it over. So I'd have minus 2 tan theta. And then I'm going to minus the root 3 as well. And we're going to have equal to 0. Now we've got a quadratic trig equation. To make it a little bit easier to see, I'm going to let x equal tan theta. So we'd have root 3 x squared minus 2x minus root 3 is equal to 0. All right, so to solve this, we've got a non-monic quadratic. So if we use our PSF method, you don't have to do it this way, but our product would be root 3 times minus root 3, which would be minus 3, and our sum would be minus 2. So then our factors are going to be minus 3 and 1. So that's what we're going to split this middle term into. So we're going to have root 3x squared plus x minus 3x minus root 3 is equal to 0. Now if I pull the x out as my common factor here, I'm going to have x outside of root 3x plus 1. Now this one's a little bit harder to see what we're going to pull out. I'm going to pull out a negative because they're both negative terms, but we want to make what's left over here the same as this. So what I'm actually going to pull out of this section as a common factor is the square root of 3. Now if we divide this by 3, we'd have 3 over root 3. If we rationalize that, we'd have 3 root 3 over 3, because we've multiplied top and bottom both by root 3, which just gives us root 3. So if we factorize this out, we're going to have root 3x, and then we would have plus 1 left over. So that one's a little bit harder to see, but we're trying to make what's in the brackets match that first one. So now we have that bracket matching, so we're going to have root 3x plus 1 and x minus root 3, and that's still equal to 0. Now if I solve both halves of that, I'm going to end up with x equals minus 1 on root 3, or x equals root 3. Now we know that x was tan theta, so we're going to have tan theta equals minus 1 on root 3, or tan theta equals root 3. Now we can solve both of those. So if we look at this one, we can draw up our all stations to central diagram. We know that tan is negative in the second and fourth quadrants. And if we've got 1 on root 3, then our related angle is going to be pi on 6. So that's going to give us theta is equal to 5 pi on 6 for this one here, or 11 pi on 6 for this one here. Now if we have a look at this one, again, our all stations to central diagram, but this time our tan is positive, so it's going to be in our first or our third quadrant. And with root 3, our related angle is going to be pi on 3. So we're going to have theta from this one is equal to pi on 3, or 4 pi on 3. So there's 4 solutions in that domain that make this equation true. So let's have a look at trig equations that involve sums and differences and double angles.